Hi, uh, welcome back to Discrete Mathematics again. Today we will continue the section set 2.1. Uh, where are we last time? Okay. Okay. Remember to join the course Slido. Once you have any questions, you can put your question on Slido. So now, story time. Give you the chance to have extra points. We just talked about the definition of set equality. So if two sets are equal, we can only if they have the same elements. Okay, so uh, please explain next time when we need to prove two sets are equal, then we can use the fact if A is the subset of B and B is a subset of A to prove that two sets are equal. How we derive these facts from the definition of set equality? Please put your answer on Slido with your name and student ID. And the first one who answers correctly will get 1 extra point. Okay, and once you have put your question on Slido, maybe you don't have enough time to answer your question. However, I will find some time to answer directly on Slido. So you may see the reply under your question. Okay. All right. Anyone can answer this question? So I think I see on Slido. Okay. All right. Okay. The event code of Slido is 2025 CC2 DGM. All right, let me repeat the question again. We have the definition of set equality. Two sets are equal. We can only if they have the same elements. So we can derive some facts directly from the definition. Once we prove two sets are equal, we can also prove the set A is a subset of B, and if the set B is a subset of A, then we can also prove that two sets are equal. How we derive the facts from the definition? Please explain. All right. No answer yet. Okay. Let's see. Only when the set has the same collection of objects, truth x in A implies x in B. Okay. So the question is, why we can have such facts? Okay, because we can prove two sets are equal by examining the elements. If they have the same elements, then two sets are equal. That's one way to prove two sets are equal or not. For other ways, we can also prove that if A is a subset of B and B is also a subset of A, then we can also prove that two sets are equal. Why? You need to explain why we can do that. Okay. We have some students says that because based on the definition of set equality for all x, we have biconditional statement if x in A, then if and only if x in B. So maybe we can separate this definition into two parts. If x in A, then implies x in B, and if x in B, then it implies x in A. Later on, we will see the definition of subset. If x in A, then x in B, then A is a subset of B. And if x in B, then x in A, then that implies B is a subset of A. Okay, so 林威成同学 alright, you can go to TA after class. Okay, so let's see the definition of subset we're talking about. If the set A is a subset of B, if and only if every element in A also in an element in B. Okay, A is a subset of B because all elements in A also in set of B. Okay, then we can use the notation this one to indicate A is a subset of B. Okay, although this is the set notation, you can consider this very similar to less than or equal to. Okay, so if you consider this is less than and equal, then you can see A is a relatively smaller set than B. Okay, so we use the notation to indicate A is a subset of B. Okay, next, based on the definition, we can see if A is a subset of B, we have such a very strong condition, even if x in A and x in B for all x's, this is true. Okay, then we can say A is B subset. Then we can see two different cases. For every set S, S is a subset of itself. Okay, so maybe we can verify for every set why A is a subset of itself. Because based on the definition, for all elements in S, then it is also an element in S, and we can say S is a subset of S. Definitely this is true, right? Because if the element in S, then the element is also in S. This is true. So we can say S is a subset of S. It's also the subset of itself. Then for empty set is also a subset of S. Okay, that's verified. Based on the definition, we need all elements in the set of the left-hand side, also the element in the right-hand side. But for empty set, there's no elements. Okay, so if there's no elements, what happens? Okay, then we can see this. Okay, maybe we can replace A and B to empty set and S. If X in empty set, then X in set S. If this is true, then we can conclude empty set is a subset of S. Okay, however, S in empty set, this is false, right? So we already know the truth table of invocation. Once the first term, if P and Q, if P is false, then no matter what value of Q is true or false, the implication will be true. Okay, so this tells us if this is true, then empty set is a subset of S. Okay, the way we prove this, we have a very special name for this. Remember? What's the name of the proof method? One extra point. Anyone? If we want to prove if P and Q, however, P is always false, that makes if P and Q true, then what's the name of the proof? Okay? English, please. It's not contradiction. It's not contraposition either. Okay? Sorry? No. Any other answer? No. Okay? Any other answer? No, it's no. Okay, once you want to prove if P equal Q, if P is always false, then we don't have to prove this equation because once P is false, then this is always true. What's the name of the proof? Sorry? No. Yeah, that's right. Vacuous proof. Remember, we have two very simple proof, trivial proof, and vacuous proof. For this one, it's just follow the vacuous proof. Because you don't have to prove anything. Because if P and Q is always false, then based on vacuous proof, then this is true. Okay, next, let's see how we show a set is or is not a subset of another set. Okay, based on the definition, if A is a subset of B, then we need to make sure every element in A, also the element in B, then A will be the subset of B. How to show that A is not a subset of B? Once we can discover what element in A that is not in B, then we can show that A is not subset of B. Okay, so this is the question I just raised earlier. Another look of equality of sets. Based on the definition, we have biconditional statement of the definition of set equality. However, we can also consider it's the combination of two positions. If X in A, then X in B, and if X in B, also X in A. Then, based on the definition of subset, we can see this is the definition of A is a subset of B, and this is the definition of B is a subset of A, and we add them together. So next time when we want to prove if two sets are equal or not, then we can examine if they are subsets to each other. Let's both these two terms are true, then we can say these two sets are equal. Okay, next one, let's see the definition of proper subset. So we have a special name proper in front of subset. So you can see it's a special case of subsets. Let's see the definition. If A is a subset of B, but A does not equal B, then we can say A is a proper subset of B. And we use the notation like this. Okay, so for, for the definition of proper subset, the size of A that equal to or less than B, because we just mentioned the subset notation, we can consider is less than or equal to. If it is not equal, it's less than B, then we can say A is a proper subset of B. Okay, then it's also make this consider true for all x is in A and x in B. Okay, so this is the definition of subset. For proper subset, we have another condition. Is this some x, x in B, and x does not in A? Okay, so this tells us the set B is larger than A, because we can discover one element x that is in B but not in A. For then downward, we can see actually proper subset just give the definition. A is a smaller subset of B. Okay, their size does not equal. So that's the definition of proper subset. Okay, so you can consider the notation of proper subset. Actually, we don't have the equal notation. We just have the less than notation. Okay, so this tells us smaller than B, but they are not equal. Okay, I hope this can help you remember the location of subset and proper subset. It's just a very similar concept to less than or equal to. However, we have different location because this is the location of subset, not less than or equal to. Okay, next, when we talk about the size, the set A is smaller than B. Actually, we can use cardinality, this term, to indicate the size. Okay, so the definition of cardinality of the finite set A are denoted by the bar of A. Okay, that's the number of distinct elements of A. Okay, so back to our previous example, A, B, C, D, E. So actually, following distinct objects of the set A, B, C, D, C, D, E. Okay, for the distinct element of this set, actually we only have A, B, C, D, E. So the cardinality of that set is 5. So actually, we can actually enumerate all elements in the set to have the cardinality of that set. Okay, so let's see the next definition. If there is exactly n distinct elements in S, and n is non-negative integer, we can say S is finite because we can actually count the number of distinct elements to n. Okay, so once you can actually count the integer n, then we call this set finite set. Otherwise, the set will be infinite because you cannot count the actual number of n of the set. So that will be an infinite set. Let's see the example below. For empty set, when we count the cardinality of empty set, we try to enumerate or count the elements in this set. For empty set, there is no distinct elements, so the cardinality of empty set is 0. Okay. Next, if S is the letter of English alphabet, then we know the set of S is 26. Because you can actually count A, B, C, D, E. Only we have 26 English alphabet in the set S. Okay, and then you can use roster method to list any elements in the set. In this case, once we have 1, 2, 3 in this set, then the cardinality will be 3. Okay, next one, last one, the set of integer is infinite. Because for integers, 1, 2, 3, 4, 5 to infinity, we cannot count the actual number of n. Okay, so the set of integer will be an infinite set. Okay, next is the definition of power set. The set of all subsets of a set A, then we denote by P of A. Okay, so once A is the set containing 2 elements A, B, then we need to enumerate all possible subsets and make it into a set P of A. Okay, so next let's see how to enumerate all subsets. We already know empty set is the subset of any set. Okay, so we will have empty set. And we know if the set S is a subset of itself. Okay, so we know AB is also a subset of set A. And then we can have different enumeration of elements. For example, we choose A into subset, but not choosing B. On the contrary, we can also choose B into the subset, but not choosing A. Okay, so totally we have 4 different subsets as the subset of A. Once we collect them all into one set, we call this set power set. Okay, based on this example, we can see if we have 8 elements in the set, and the power set, the cardinality of this power set is 2 to the power of n. Because you can see for this 4 subset of power of A, you can see for element A, you can either choose or not choose the element into the subset. Okay, so once we don't choose A, we don't choose B, then it will be empty set. Once we choose A, not choose B, it will be subset A. Once we choose B, not choose A, then it will be subset B. Once both elements are chosen, then we have a subset AB. Okay, so for each element, we have different choices. So if total number is n, then we will have 2 to the power of n different subsets of the power set.你说包括怎么样？对，不一样。因为我们的空集合是 empty set，所以我们不会用花号空集合，因为花号空集合是某一个集合包含空集合的这样的集合，它跟空集合的意义是不一样的。所以在这个问题里面，我们要说空集合是所有集合的子集合，我们要用空集合，不能用花号空集合。好。Okay. The other way to consider empty set, and this set is different. Maybe we can consider its cardinality, right? If their cardinality are different, then we can consider they are different set. We have empty set. We also have a set contains empty set. Okay, so we already know the cardinality of empty set is 0. What's the cardinality of this set? 1, right? Okay, so you can see the cardinality of these two sets are different. That implies these two sets are not the same. Okay. Next, let's see the definition of tuples. Okay, tuples means order collection of objects. Okay, so for order n tuples A1, A2 to AN, we have such order collection of objects A1 to AN. Okay, so we call this ordered n tuples. Based on this definition, we can have two tuples. Okay, because once we only have element A1 and A2, then we call this two tuples because the number of A is 2. We can also call this order pairs because A half is order and the element 2 number is 2. Then for two n tuples are equal, you can only if their corresponding elements are equal. So once you have A1, A2 to AN, we have another n tuple B1, B2 to Bn. If we want to prove that these two n tuples are equal, then we need to prove A1 equals B1, A2 equals B2, AN equals Bn. That's the way we prove two n tuples are equal. Okay, then based on the definition of tuples, we can derive the definition of Cartesian product. The Cartesian product of two sets A and B, we use the notation cross to indicate the Cartesian product of two sets. That will be the set of order pairs A, B, when A intersect A and B intersect capital B. Okay, so Cartesian product, actually we can write into the form of set. We collect all these two tuples AB into this set, and it follows the property A is A and B is B. Okay, as we can see the example, once capital A is AB and capital B is 1, 2, 3, then Cartesian product of these two sets will be the collection of order pairs. Okay, then the first element must come from A, and the second element must come from B. Okay, so if the cardinality of A and B is 2 and 3, then we have six different order pairs. Okay, once we put them into one set, then that will be the product of the set A B. Okay, so once we have such conditional product, actually we can discover a subset because you can see for the conditional product A B, we have six different elements. We can discover a subset. We call this relations from set A to set B. Okay, so you can discover more discussion about relations about two sets. Okay, we just use order pairs to describe the Cartesian product example. However, we can make it more general. The Cartesian product of set capital A1 to capital AN, we have n different sets. Then the Cartesian product of this n different sets will be A1, A2 to AN if A1 in capital A1, A2 in capital A2, and so on. Okay, so next time I will see the exercise condition product A, B, C. For A is 0, 1, B is 1, 2, and C is 0, 1, 2. Then you can discover all three tuples of this condition product. Okay, next one, let's see the definition of true set of quantifiers. We can combine the definition of quantifiers or what we have learned in chapter 1 logic with the set definition. Given the predicate logic P and its domain D, we can define the true set P once the set of elements in the domain D that makes P of X is true, then we can collect all X into the set. That is called the true set of predicate logic P. Okay, so in the definition of true set of quantifiers, we can collect all X in the domain D with the property P of X is true. Okay. Let's see the example. In the true set P of X, where the domain is integers and P of X is the absolute value of X equals 1, okay, then we can collect all X in the domain that follows the predicate. The absolute value of X is 1. So eventually in this set, we will have -1 and 1. Because for the domain of all integers, only -1 and 1 follows the property is absolute value X equals 1. Okay, next let's see this practice. If your concept of elements, set, subsets, and proper subset is clear enough. Okay, so first one, let's see. Determine whether the statements are true or false. Empty set is an element of that set. Okay, so if you want to determine if something in the set, then you can discover or consider this is the elements. If this element appear in this set, okay, so actually we can discover the element here. Okay, so the answer of this statement is true. Next, if this elements in this set, okay, so actually in this set, we have only one element, empty set, but we cannot discover one element of this. Okay, so the answer is false. Okay, next, if we can discover the element in the set of this, yes, because once the element is this, then we can actually discover the element is here. Okay, so the answer is true. Okay. Next, let's see if the set contains empty set is a subset of this one. Okay, so once we want to determine if it is the subset of another set, we can follow the definition of subset. Every element in set A must be in the set B, then A is a subset. Okay. So in this set, we have only one element, empty set. So is this empty set also an element of set B? Yes, because we just discovered we have an empty set as an element in set B. Okay, so B is true. Okay, next, if this set is a proper subset of this, okay, so for proper subset, we need to verify if A is a subset of B and the size of these two sets are not equal. Okay, so you can discover one element in B and A. So let's see. The first thing is this set is a subset of this set. Okay, once we evaluate the subset, we need to make sure every element in this set A also in set B. So we only have one element in this set. And that's a set contains every set. So can you discover this element in this set? Yes, right? Because we can discover the elements here. So we can make sure set A is a subset of set B. Okay, next one, can we discover one element in B but not in A? Yes, because we have empty set here. Okay, so we can consider this set is a proper subset of this one. Okay, the next one is easy because we can see the element is the set contains every set. So we can discover the element here. So it's a subset of this set. But for set B, we only have one distinct element, this one. We cannot discover another element X in B, but not in A. Okay, so actually, this one is not a proper subset of this one. Okay, so if you remember the definition of elements, set, subset, and proper subset, actually you can use the definition to evaluate all these statements to see if it is true or false. Okay, any questions so far? Any question about this exercise? 有问题吗？不知道我在讲什么，其实。好，那我用中文再解释一次啊，好，那我把这些东西都擦掉好了，好。好，我们这边呢是让同学来判断这个某一个元素是不是在另外一个集合里面，或是某一个集合是不是其他集合的 subset 或是 proper subset。所以你只要 base 在这些东西的 definition 上，好就可以来做判断。好，那我们看第一项，就是这个元素是不是属于这个集合？那只要看这个集合里面有没有这个元素就好了。那这一个元素有没有在这个集合里面？有嘛？好，我们的元素是空集合，然后我们真的找到有这个元素在这个集合里面，所以这个东西就属于这个集合。好，那 B 呢？这一个元素有没有在这个集合里面呢？没有嘛？好，因为我们这一个集合里面只有一个元素叫空集合，它并没有一个元素叫做包含空集合的集合这个东西，所以这个东西并不在这个集合里面。好，所以第二题就是错的。好，那第三题我们再验证一下，这个东西有没有在这个集合里面呢？有嘛？好，因为这个集合里面唯一的一个东西就是包含空集合的集合，所以实际上这一个 element 有在这个集合里面。好，那接下来我们在判断 subset 的时候，子集合的时候，我们要确定的就是在子集合 A 的元素是不是都在子集合 B。好，那假设我们把这一排都叫 子集合 A， 这一台都叫 B。好，那我们就来看看这个集合里面的元素有没有在这里面。那这个集合里面的唯一一个元素呢，就叫空集合。空集合有没有在 B 里面？有嘛？好，在这啊，好，如果在 A 的元素全部都在 B 的话，那 A 就是 B 的子集合。好，那接下来的这个呢是问它是不是一个 proper subset。好，那 proper subset 的定义是 A 是 B 的子集合，而且 A 比 B 还来得小。来得小的意思就是你可以找到一个 element 在 B， 但是 A 里面是没有的，那 B 就比 A 大嘛。好，那所以我们先确认一下它是不是它的子集合，看看这个元素有没有落在这个里面。有吗？好，所以这个元素有在这个里面，所以它是它的子集合。那我们能不能找到另外一个元素在 B 不在 A 呢？也有嘛。好，空集合这个东西是在 B， 但是不在 A。好，所以实际上这个一的这个答案，好，它是它的 proper subset 就是对的。好，那我们看最后一题，这个 proper subset 确认一下这个东西 A 是不是 B 的子集合？是嘛？好，因为它的元素是这一个，这个元素也有出现在 B 里面。好，所以所有出现在 A 的都出现在 B，A 就是 B 的子集合。那我们能不能找到一个在 B 里面的元素是不在 A 里面的？找不到嘛？好，因为 B 元素总共只有这个东西而已，这两个东西是一样的。好，所以实际上 B 这个集合的 element 只有这个东西而已。好，所以实际上 A 只有这个东西 ，B 也只有这个东西，我们没办法找到在 B 不在 A 的东西。好，所以 A 是 B 的 proper subset。好，这样应该够清楚了吧？好，好，那我们就看一下这次的 homework assignment. So it's due 2 weeks later. We have just a few questions for you to exercise. Okay, this one. All right. Next, let's jump to section 2.2. It's about set operations. Once we have the definition of set, then we can have different operations between two sets or more. Okay, for example, union, intersection, complementation, difference. Okay, I believe you have learned this before, so we can give a very quick review of what's its English name and how we describe in propositional logic. Okay, so the definition of union of two sets. So we use the notation union. Okay, so the definition is if X in A or X in B, then we collect all X into the set of the union set of A, B. Okay, so based on the Venn diagram, we can see this is the scope of set A, this is scope of set B. And if X in A or X in B, we can also include this element into the union set. So that's the definition of union. Okay, so let's see, if A is 1 to 3 and B is 3, 4, 5. Okay, then the union of these two sets, we include all distinct elements into the union set 1, 2, 3, 4, 5. Okay, next, intersection. If X in A and X also in B, then we can include all such elements into the interaction set of A and B. Okay, so for the Venn diagram, if the element in A, if the element also needs to be in B, okay, so we have the scope here. If the element is here, then it's both in A and both in B, then that will be the intersection of the set A and B. For this example, 1, 2, 3, and 3, 4, 5. Okay, so we can see the intersection of these two sets is only element of 3. Okay, so we have another name for two sets if the intersection is empty. Because you can see, once these two sets have the region overlapping, then this is the intersection region. However, if we have two circles with no overlapping. Okay, then we cannot find any elements both in A and both in B. We call these two sets disjoint set. For example, 1, 2, 3, and 4, 5, 6. Okay, so we cannot find any elements both in A and both in B. Therefore, its intersection is empty set. For complement set, we usually use the notation A bar to indicate if A is a set, then the complement set A is U minus A. Okay, so if the scope of A is here, then we use U minus A, the universal set, minus B set, then it will be A complement. Okay. So the complement of set A, sometimes we use the notation A, C. Okay, is the set of set A. Okay, then we can see this example. If U is an integer less than 100, then the complement of the set X larger than 70. Okay, so you can see the universal set is integer less than 100. So starting from 99, 98, 97, and so on. And what is the complement set of X larger than 70? So we need to exclude all elements for this set. That will be the set X less than and equal to 70. Okay, we collect all these X together. That will be the complement set of the original set. Definition of difference of set A and set B, we use the notation A minus B to indicate its difference. The definition is the element in A but not in B. Okay, so this is the Venn diagram. Once we have scope of A, then we need to exclude all elements that's in B. Therefore, we have the range here. Okay, we call this difference. Okay, so for the definition of A minus B, actually we can collect all elements X, X in A, and X not in B. Okay, so for X not in B, actually we can write its complement of B. Okay, so A intersect B complement. Okay, so these two sets are equal. Okay, then let's see the definition of cardinality of union of two sets. Okay, if you want to count the number of elements in the union set of A and B, okay, then the cardinality will be, we can count the cardinality of A first, plus the cardinality of B, and then you can see for the intersection region, we count twice. Okay, so we need to minus the intersection of this area to see what is cardinality. So we use cardinality of A plus cardinality of B minus the cardinality of A intersect B. Okay, just a few easy examples to review the definition of these operations. If the universal set is 0, 1, 2 to 10, and A is the set 1 to 5, and B is the set 4 to 8, then the union of A and B, remember, X in A or X in B, okay? It can appear both in set A and set B, so the union of this set is 1 to 5 to 8. Okay, so 1, 2, 3, 4 to 8. The intersection of A and B, the element should be both in A and also in B. Okay, so the solution is the set of 4 and 5. Next, A's complement, okay, is not in A and in the universal set. Okay, we use universal minus A, it will be complement of set A. So we need to discover all elements not in A but in the universal set. So it will be 0 and from 6 to 10. Okay, and A minus B, the element in A, but not in B. Okay, so you can see what you can check if one in A and not in B. Once it follows, then it's in the set A minus B. Okay, so we have the elements 1, 2, 3 in A, not in B. Okay, if B minus A in element in B but not in A, okay, so it will be 6, 7, and 8. Okay, next let's see the definition of symmetric difference. Okay, we use a Merge spatial notation plus with a circle to indicate a symmetric difference. So the definition of symmetric difference is A minus B union B minus A. So we already know the Venn diagram for A minus B is the region here, and B minus A is the region here. And we union this broad regions together, that will be the symmetric difference of A and B. Okay, so let's see the example. Once we have the universal set from 0 to 10, and A is 1, 2, 3, 4, 5, and B is 4 to 8. And we need to discover the elements in A and in B. Okay, so in A and in B, it will be 1, 2, 3. Then we union element in B and in A. Okay, in B and in A, it will be 6, 7, 8. Okay, so these 6 elements after union, we will have the set 1, 2, 3, 6, 7, 8. All right. For set, we also have set identities very similar to propositional logic. So we have identity laws. If A union empty set, it will be A. A intersect universal set, it will be A. So we call this identity laws because after this operation, the set A still is himself. Okay, next one, domination law. After the operation, the results dominate by U or empty set. If we use A union uniset, a universal set, then the results will be universal set. A intersect empty set, it will be empty set. Okay, so we can see the results is dominated by universal set U and empty set. Next one, identity laws. Okay, it's just like 2 times 2 times 2. Okay, so we can also apply this operation to set. If A union A is still A, A intersect A, it will be A. Complementation law, we have complement of complement A, it will be A. Okay, so for set identities, we also have uh, commutative laws, associative laws, and distributive laws. Okay, so for commutative laws, we can switch their position and the results remains the same. If A union B, then the set equals the set B union A. And for associative laws, we can associate application for different orders. We have A union B union C. You can union BC first or union AB first. The results remains the same. We call this associative loss. For distributive loss, we can use A intersect B union C. Okay, then the results equals to A intersect B, and the results union A intersect C. Okay, so we can see this is very similar to propositional logic. We can also apply De Morgan's law. Once we have the complement of A union B, then you can consider union, you can consider the complement as the negation of the propositional logic. Okay, so by De Morgan's laws, once we have negation of A union B, we will have complement of A intersect complement consider negation equals the operation of complement, then the results will be very similar. Okay, therefore, our social laws, A union A intersect B, the result will be A. Okay, so based on Venn diagram, our social laws will be really easy because once we have A intersect B based on the Venn diagram, so we can see the intersect, the overlapping area. If we reach the overlapping area to union A, okay, the results still A. Okay, then we can see it's a little bit difficult to explain absorption laws in positional logic, but it becomes easier in stack operation. Okay, next one, complement law A union complement A, it will be the universal set. Okay, so I believe this is no problem because A and complement A, after union, it will be universal. The intersection of these two sets will be set. Okay, then based on these set identities, then we can prove two sets are equal or not. Okay, so next we will see how to prove set identities. Okay, because we have a lot of set identities listed here. So actually we have the set in the left hand side and we also have the set in the right hand side. We need to prove two sets are equal. Okay, so next we will see three different ways to prove set identities. The first way is to prove each set is a subset of each other. We just mentioned how we prove set equality. Okay, so we can prove A is a subset of B and B is a subset of A. Then we can say A and B are equal sets. Okay. The second way is to use set builder notations and propositional logic to prove that the set A equals set B. Okay, because we will derive in each step the set are equal until A becomes B. The last one is use membership tables to verify that elements in the combination of set always either belongs to the same side or not. Okay. Let's see more example here. Okay, if we want to prove second De Morgan's law, A intersect B complement is equals A's complement union complement of B. Okay, then let's see. Let's try the first method to prove that A is a subset of B and B is also a subset of A. Then both sets are equal. Okay. For the first case, we prove the left-hand side is the subset of the right-hand side. Okay. And then remember the definition of subset. If the element in A is also the element in B, then we can prove that A is a subset of B. And therefore, we choose by the definition of subset. X in the set of the left-hand side, X in A intersect B complement. Okay. Then we can rewrite this set to because the complement of A intersect B. So in this set, then X does not in A intersect B. Because the set A that is complement will be disjoint set. Once X is complement, then X will not in A intersect B. Okay. Then if X does not in A intersect B, then we can rewrite A intersect B by its definition. X in A and X in B. Okay. So this is the definition of X in this set. However, for the second step, X is not in this step. So we have a not in front of these terms. Okay. Next, we can rewrite this procedural logic by De Morgan's law because we have a not in front of the parentheses. So we put not inside this parentheses. We have not X in A and change intersection to union. Okay, so now we have not x into A, which means x not in the set A, okay, or x not in the set B. Okay, so if x not in A or x not in B, then we can have x in A bar and x in B bar. Because once it is not in A, then it will be in its complement. So x in complement of A. Okay, and then we follow the definition. Once x in A bar and x in B bar, this is 4. Okay, so that's will be the definition of union, right? X in A bar or x in B bar. So x in this the union of these two sets. Now we derive the results because we can show that once x in the right hand side set, then x also in the right hand side set, then we can claim that the set in the left hand side is a subset of the set in the right hand side. That will be case 1. For the second case, it will be easy. Once we have the previous steps, you can just write the previous step in the reverse order. Then we can derive if x in the right hand side, then x is also on the left hand side. Okay, so once we have A is B subset and B is also subset of A, then we can prove that they are equal sets. This is the first method. Okay, we prove that each set is a subset of each other, then we can prove the set identities. So you can use this method to verify all these set identities. Okay, to see if you can derive the steps to prove that they are equal sets. Okay, the second method is use set builder notations. Okay, so we will write these steps using set builder notations. So for the complement set of A intersect B, then we can use the set builder notation. We collect all x into the set, follow the properties x not in intersect of A and B. Okay, that's the definition of complement of the set A intersect B. Okay, then you can see the following steps are just very similar to the previous one. But instead, we set up these steps using step notations to derive equals sets in each step. In the end, we can transform the right-hand side set to the right-hand side. Okay, next, based on this definition and set operations, let's see this example, how we prove that if we have ABC sets, okay, and given the condition A intersect C is a subset of B intersect C, and A intersect C complement is also a subset of B intersect C complement, then we can derive the fact that A is a subset of B. Okay, so actually, intuitively, this is right because you can see based on the premises, we have two premises. A intersect C is a subset of B intersect C. Okay, and A intersect C's complement is a subset of B intersect C's complement. We just have actual set C and C's complement of these premises. So intuitively, you can consider A is a subset of B. Maybe it's correct. Okay, so let's see the solution. How we prove this? Okay, remember when we need to prove A is a subset of B, we can use the definition. If X in A and X in B, then we can prove A is a subset of B. So we can choose an arbitrary instance X in A. Then for the next steps, we need to prove X is also in B. Then based on the definition of subset, we can see A is a subset of B. Okay. Next, we can prove that cases because we have C and C's complement. Okay, so next we divide the step into two different cases. Once X in A, then we need to consider if X in C or C's complement. Okay, for the first case, we consider X is also in C. Okay, next let's see what happens. If X in C, then by the original versus X is also in A. So we can see X in A and X also in C. Then we have X in intersection of A and C. So this is apparently correct, right? Because we have the set A and we also have the set C. Now we assume X in A, and for case one, we assume X in C. If X in A and also in C, then it will be the definition of intersection, right? So X must be here. Okay, so we can write X in the intersection of A and C. Okay, then let's see the premises of the question. A intersection C is a subset of B intersection C. Okay, then if X is A intersection C, then based on the premises, the subset is also in B intersection C. So we can write X also in B intersect C. Okay, that's the definition of subset. Let's see, once we have B here, we have C here. If X in the intersection of B and C, X is here, then definitely X in B, right? Because X is located in this region. Once X is in the intersection of B and C, then X must be in B. Okay, so in this case, we have X in A and X also in B. So we can claim that A is the subset. That's the way we finish case one. So for the next one, case two, what happens if X not in C? Okay, if X not in C, then X is C's complement, right? So once X is C's complement, then we already know X in A. Then X in A and X also in C's complement, then X will be in the intersection of A and C complement. And by definition, by the premises, A intersection C complement is a subset of B intersect C complement. So if A is subset, then X in this set, X will also in the set of the right hand side. Right? So X is also in B intersect C complement. Okay, so let's see. If we have B here, we have C here. So what happens X in B intersect C complement? Okay, so this is C. So C complement is here, right? So this is C complement. And the C complement intersect B. Okay, so that will be this area. Okay, once X in B, the intersection of B and C's complement, then X also in B. Okay, so then we calculate the second case. If X in A, then X also in B. So for I combine these two cases, then we can derive A is a subset of B. 可以吗？ 还需要用中文讲一次吗？好，需要吗？好，不用的话就 OK 了。好。All right. Let's see generalized union and intersection. Previously, we only see two sets A and B, and A union B and A intersect B. However, we can extend this to A1, A2 to AN. We call this generalized union and intersection. So we can use this equation to indicate we have the union operations for the index I to n. So once we have I from 1 to n, so the union applies to A1, union A2, union to AN. Okay, for the intersection AI, we can also have A1 intersect A2 to AN. Okay, so let's see this step. Once we have I equals 1, 2, 3, we use the ellipsis notation, right? This means I is an infinite number. And if the definition of AI is I plus 1, I plus 2, ellipsis. Okay? Then what is the union of AI when I is 1 to n? Okay, so in this case, what is A1? Okay, A1 is I plus 1, I plus 2. So we have 1, 2, 3, and to infinity. And then what is A2? Actually, A2 starts from 2, then I plus 1, I plus 2. So we have 3, 4 to infinity. So you can list A1, A2, A3 to AN. Okay, so that will be the union of all these sets. So it will be 1, 2, 3, 4 to infinity, union 2, 3, 4, 5 to infinity. So in the end, the union will be 1, 2, 3, 4 to infinity. Okay, so let's see the intersection of AI from A1, A2 to AN. Okay, so we already know that A1 is 1, 2, 3 to infinity, and A2 is 2, 3, 4 to infinity. So what is the union of this set? What is the intersection of the set? Okay, so you can see the intersection of this set will be 2, 3, 4, 5, right? Then we also have A3, A4, and A5. So you can see after the intersection of the other set, we will have gradually, we need to remove one element. Because in this case, the intersection of these two sets, we remove A. Then once we have A3, then will be 3, 4, 5, 4. So we will remove 2. For A4, we have 4, 7, 6. Then we will remove 3. So in the end, the intersection of these n sets will be n plus 1, n plus 2 to infinity. That will be an. Okay, very simple case for the generalization in generalize the union and intersection. 好，那我们还有3分钟哦，就看看同学对这个单元有没有什么问题。好，我看一下那个 slide 上面同学有没有什么提问哦。好 ，power set of 空集合的集合是只有空集合还是空集合跟空集合的集合？好，那我们看一下power set of 空集合的集合。好，所以假设我们现在有一个集合叫 叫做空集合的集合。这个集合的 power set 是什么？好，那这个集合 power set 呢，实际上就是我们要不要选空集合到我们的 set。好，所以当我们不选这个 set 的时候呢，它就是这个空集合。当我们选了这个 set 的时候呢，它就是空集合吗？好，选了这个 set 还是空集合？好，所以这个集合的 power set 呢，应该就是长这样哦。好，实际上就是包含空集合的集合。好，那我们来验证一下，我们刚刚说 power set 的个数呢是2的 n 次方。好，当我们的集合里面有 n 个东西的时候，我们实际上就会有2的 n 次方个 subset 落在这个 power set 里面。那实际上这个空集合里面的集合的 element 是0个，好，所以实际上它的 power set 呢就是2的0次方。好，所以它的 power set 里面只会有一个东西，这个东西就是空集合。好，那这个是这个同学的问题哦。好，没有打破2的 n 次方的规律哦，还是符合2的 n 次方的规律哦。好，那个 A 有的元素 B 都有 ，B 的 A 也有，那两个就相同。好，这个应该就是两个集合相等的定义哦。好，那应该没有其他问题了，我们今天就到这边下课。OK，see you next time。哎，
就是我讲，就是可是它不是，怎么讲？它不是有空集合和集合，
对，
所以它那个就是怎么讲？它的数量不是一嘛，因为它有空集合这个集合，不是空集合才是。
所以刚的问题是 power set of 空集合的集合。空集合的集合是指包含空集合的这个集合。
对啊，那这样它数量不是一吗？
不
是只有空集合。
不是，所以我先确认一下，这个问题是在问空集合还是包含空集合的集合？
包含空集合的集合。
包含空集合的集合就是写成这样吗？
对，就是刚刚不是说就是空集合而已，就没有旁边这两个括号的这个它才是0，然后
对，
它这样的话，那这个为什么不是1？对，因为它这个也是，就是这个不是也是一个元素吗？那为什么它不是1？然后如果是1的话，那2的1次方不就是
？OK，所以假设我们选了这个元素到 subset 里面，
对，
这是一个集合嘛？
对，
所以它可能就会变成是，所以应该是这一个啦。当我们选进来之后，它的 subset 就变成这一个。那假设不选的话，就是这一个这样。对，没错。不好意思，很好，谢谢。好，有什么问题？没有什么。好。对，没错，4月9号上课时间。245可以再讨论看看。对。
问题，最开始问题的回答就是 A implies X 属于 A implies X 属于 B， and X implies B， 不是 X 属于 B implies X，
对，
那是对。
你讲的这个其实是我的问题。对，我要问的问题是说，为什么集合相等也可以等同于这件事情？要解释这两个东西为什么是相等的这样。那你讲的这件事情其实是我的问题这样。好。没有。你这样子可以。上次没有点到你。对。但是老师上次是先把所有人都出席先勾起来， 然后点名的时候没有点到名字，我才会把出席改成是缺席这样，预设全部都是出席这样。所以如果你被改到缺席的话，那是不是上次没有点到啊？还是你上次有来？
我上次有来，
但是没有点到名，还是没有听清楚名字，还是怎么样？好，没关系，我帮你改一下好了。
就是他们说上礼拜二的时候
点名，
就是刚刚有两位同学，
所以会不会是那个啊？就是我勾全部都出席，但只有第一页，没有第二页、第三页。
我没有用过那个点名的系统。
哦。OK。好，那没关系好了，我们就把第一次点名就全部都取消好了，好，没问题，好，有什么问题？OK，没关系，没问题，好，就是他们两个都是 subset， 但是如果是 subset 的话，有可能 A 会跟 B 一样大，所以才会有像小于等于的感觉。但是没有下面那个的话，就是它没有等于 A 一定比 B 还小，但它也是它的子集合这样。
所以就是有这个的话，就是可以。
就是 A 是 B 的子集合，但是 A 有可能小于它，有可能跟它一样大，都有可能这样。
好，所以就是这个就是一定不会让它改。
对，没错。所以你那时候那已经算高了。但是去年好像同学对于考 A B 都觉得，对吧？对，今年再看看。